everyone, and welcome. The time is now 12 o'clock p.m. Central Time. I'm going to be your host, Dr. Matthew Richardson, and this is actually going to be a fusion between Daily Space and Astro 101, as both Andreas and Pamela are currently unavailable because they're traveling. So give me a quick second to make sure things are good on the Twitch side of things, and we'll go ahead and get started. All right, I'm already there, and do I have chat? Let's see if I have chat. I believe I have chat. All right. Hey, Tom. All right. Well, I see that one person's there and I can see everyone else. Hello, Hanny. Let's go ahead and get started, guys. So, today's story, which is kind of like going to be a mixture of the typical daily space news updates, combined with a little twist of Astro 101. But today's story, we're going to start off with talking about what we see here in front of us, which is basically a list of pulsars and binary systems. Hey, Guido. And so, hey, Susie, thanks. And so, the key thing I want to say about this is that it's not uncommon for stars to live in binary systems. In fact, I mean, many stars in our galaxy are in binary systems. But specifically, I want to concentrate on these particular types of systems where we know at least one of the components is a pulsar, or another way of putting it is a neutron star. Now, as we scroll through this list, and if I can find there we go, as we scroll through this list, and if you look at the fourth column from the left, it basically gives you the different components of the system along with their masses. And of course, we know that one of the stars is going to be a neutron star, or a pulsar is another name for it. But basically a neutron star, and then there's the other component. But as you scroll through the list, many of the companion stars in these systems are either unknown or of solar type or brown dwarfs. You rarely see the case where there's going to be a neutron star, and its companion is also a neutron star. Unless you run into the case that we see here, that I've highlighted. But there's very few of them. In fact, I've read that since their discovery, well, not their discovery, they've been around forever, but since they were first observed sometime back in the 1970s, only somewhere around 16, and I mean this is 16 at the time of the article that I read, 16 neutron binary systems had been discovered out of this list, which was composed sometime back in 2005. So it's quite interesting to think about that there's very few of these systems being found. And we're going to kind of get into not so much the why, but another question involved with these particular systems. But of course, we know of these systems. We know of these systems because of the fact that they serve as great ways to be able to, of course, test general relativity. If you guys can remember, a little bit over a year ago, I believe it was the LIGO instrument that observed gravitational waves from two neutron stars in a binary system that were undergoing the process of colliding into one another. And of course, during this process, they produced neutron gravitational waves. Now, these systems are, of course, important not only for just being able to test general relativity, but if you think about it, the process that goes into producing these stars, that is the supernova type 2 of the red giant that died in order to produce these stars, that process is highly important in being able to enrich the galaxy with materials that are being able to spread across the galaxy and produce things such as us. So Neutron stars are very important. Um, they, of course, are birthplaces of materials that are going to be much heavier than iron. Um, but one of the key things that, and this kind of brings us into the actual story for today. One of the key things is still a mystery. Is exactly how do you get a system composed of two neutron stars, right? Just thinking about the fact that to produce a neutron star, you'd have to have underwent some sort of the red giant that was used to produce the neutron star has to have underwent a supernova type 2 explosion. Imagining that happening within the same system is very difficult. How would the system remain stable enough to be able to remain as a neutron-neutron star pair? And so when I first was looking at the story and reading through it, I mean, even before I got to the part where they were able to present a solution to this problem, I was thinking to myself, well, okay, well, let's just think about this, very basically. And so I'm going to go ahead and scroll down. Well, not scroll down, but I'm going to now also bring in the Astro 101 portion of today's discussion. And so I was wondering exactly, well, how much energy would it require to physically move the star, right? Let's just even assume that the first star goes the first red giant in the system goes supernova. Now, at that moment in time, its companion is either a red giant or still in the main sequence. Um, and when it goes supernova, because of the fact that its companion is either a main sequence star still or a red giant, it's fairly massive and probably can withstand the blast, and still remain in a stable system. However, with the second explosion, we now have a neutron star and a red giant, and this red giant explodes. Well, this neutron star, while dense, is fairly light, right, compared to its companion. And what I was wondering was, well, once this star goes supernova, will the dynamics of the system be such that the explosion can physically push away, give the neutron star enough energy to eject it from the system? And so, and so, I decided to do a quick calculation, as I typically now do for Astro 101, to see exactly is it plausible for this process of the second star, the red giant going supernova and being able to push away the neutron star. I mean, of course, in my mind, I was thinking, of course, no, right? But let's see what the math tells us. So I did a quick calculation, and I basically set up the situation I just described. And my assumptions are that the red giant is about 10 solar masses. These are typical values, of course, that we can get for these types of stars, like red giants, 10 solar masses, neutron stars, 2 solar masses, radius of neutron star about 14 kilometers, somewhere on the order of like the low tens of kilometers. Separation of the system to be about 2 AU. This particular separation I got from that web page I just previously showed you guys with the list of pulsars and binary systems. And lastly, I just looked it up online that the typical Type 2 supernova releases an average energy of 10 to the 44 joules. And this is the total energy, actually, not average, but total energy. And so I'm just going to assume in this case that when the supernova goes off, all of that energy is released at once instead of over some period of time. And so the very first thing I was thinking about doing was, well, I would love to know exactly, well, what is the gravitational attraction between the neutron star and its red giant companion before there's any sort of explosion, supernova type 2 that occurs. And so we can go ahead and utilize the potential energy formula, gravitational potential energy formula, given the assumptions that we've assumed, we get somewhere on the order of 10 to the 40 joules of potential energy. And essentially, this is the amount of energy that would be, at the very minimum, the amount of energy that we would require to break the system apart. And so, continuing on from there, and again, we're assuming though, when the red giant goes supernova, that all of this energy is just, it expands away the that star, excuse me, all at once. And so the key thing we have to realize here though is that the energy is not like, it's not directed. It spreads uniformly in all directions. And so we have to take that energy, that total energy that's released, and we have to spread it out over a spherical surface. Now, when that occurs, of course, only a small fraction of that spherical surface will actually come in contact with our neutron star. So in this situation, I'm assuming, of course, that when the blast occurs, we have particle radiation going in all directions, we have photons going in all directions. And it's these things, that are pressing up against our neutron star that will cause it to undergo some sort of movement away from the supernova, the point of creation of the supernova. And so we have to take that into consideration with our calculation. So I calculated the fractional amount of area of that total spherical surface that corresponds to the area that the cross-sectional area that the neutron star would take up, and multiplied that times the total energy output from the supernova. And so basically, just looking at that, I end up getting something on the order of 10 to the 28 joules of energy. And just looking at that and comparing it to the amount of gravitational potential energy between the two stars prior to the explosion, I'm seeing that, well, it's really small actually. It's 12 orders of magnitude smaller. But then I started thinking, well, actually, true that there's this energy that's pushing, it's being used to push away the neutron star. But when we no longer have a system in which we have a red giant and a neutron star, we actually now have a system that's a neutron star pair. And so I decided to continue my calculations, um, and just go with the assumption, of course, that the new neutron star that's been produced, its physical characteristics are not that much different or very similar to the first neutron star that was created in the system. And so even with this, even under those assumptions though, and keeping all else for the most part the same, we get something on the order of 10 to 39 joules of potential energy between these two neutron stars. And just comparing it, of course, to the 10 to the 28, it's still 11 orders of magnitude smaller. That is the amount of energy that's being produced within our supernova. And so it's clear, though, to me that this isn't enough energy, of course, to just outright push the neutron star away. But maybe it's plausible, given the math that I've worked here. Maybe though that amount of energy would be useful, or could be used in being able to disrupt the system in some sort of way. And those are my initial thoughts, even before actually getting through the entire article that I was reading. And the article that I was reading was sent to me via email, and I got it this morning at this morning sometime. And so did the quick calculation, and now we can go ahead and continue on with exactly how could we have these types of systems, at least what the scientists believe could be happening within these systems. I'm going to take a moment to look at questions because I've been like talking and talking and talking. So yeah, wow, only 2 AU between stars, and I got that from here actually. So if I scroll, well, let's do this. Let me change the scene. There we go. And so if you look at this list of pulsars and binary star systems, it wasn't this one, but I think it was. Where were you? See if I can just quickly find it, and hopefully, here we go. So for this particular system, composed of a neutron star and a supergiant star. The distance between the two stars, though, in this particular system is 280,000. I'm sorry, 280 million kilometers, which is roughly almost equal to two AU, because a single AU is about 150 million kilometers. And so this particular distance is actually, from my understanding, kind of like reasonable. And so, looking at comments really quick. So, Finring is asking a question here. Um, Hopefully, Annie, before I get to Finnering's question, hopefully, Annie, I've answered some of your questions there. How much of that energy will affect the neutron star? Um, I hope I answered that within the quick bit of math that I showed there. And what about the neutron star being moved by the bigger star's mass loss? So yeah, that was I think that was also a part of the calculation that I just did. And so Finring is asking, now that we know that the neutron stars are main sources of heavy elements, does that make the island of stability in periodic table less likely? Because we don't find any long-lived radioactive elements heavier than thorium and uranium in nature. And so, if I'm understanding this correctly, um, and so the island of stability corresponds to, if you were to look, for example, at various isotopes of different atoms, only certain isotopes are going to be considered to be stable. And this is going to be based off of the number of neutrons relative to the number of protons that are within the nucleus of the atom. Does that make the... And so I'm thinking that I mean, honestly, I don't know the answer to the question, but I'm assuming that that particular island of stability is... So I guess the question would have to, I guess the main thing would have to be that we'd have to be able to actually like get close to a neutron star and see if we're able to find if we're able to find particular isotopes of the really heavy elements and see if they are stable versus, like, compared to what we've assumed them to not be for certain types of isotopes that are within that island of stability. Um, and I don't know. I don't think that's actually going to be very plausible, especially not like within the near future or anything like that. But honestly, I don't know. I mean, I think that island of stability is it's a lot of it's based. Some of it's based off of observation, of course. Some of it's theoretical. Um, but yeah, I honestly just don't know. Oh, you are. That's that's pretty cool. Um, but yeah, I guess, I mean, the only way you really know is to be able to observe, right? Which would require us being within the vicinity of a neutron star. And so Haney states, what about the effect of all that matter falling onto a neutron star on one side? Would that be explosive? All right. So I think what Haney's getting at here is the idea that if the neutron star were to accrete the mass, now neutron stars, like white dwarfs, do have a mass limit. Um, if the neutron star were to accrete the mass, I think one of two things would happen. You either have the situation of the neutron star beginning to speed up, or you have the condition where the neutron star will, I believe it will undergo like a white dwarf that reaches the Chandrasekhar limit. It will undergo it will undergo some sort of supernova and probably collapse into a black hole or something like that, depending on like the mass of the neutron star prior to collapse or destroy itself. I mean, I don't honestly don't know. But I think in that scenario though, you're required for the mass to be accreted slowly. I think in this situation, you're kind of having like a bunch of stuff just slamming into the neutron star, and I don't know, I don't think it's actually going to be able to like accrete for example, in a system where the neutron star is able to suck, you know, material off of its companion star over some longer period of time. I'm sorry. I apologize. Have I? Is it not clear what I'm saying here? Hey there, Rocking Donut. You're actually new to the stream. I haven't seen your name before. And I don't get much of this, but it's very well. I'm happy it's very interesting. But if I'm not explaining something that or something doesn't make sense, by all means, ask questions, and I will try my best to explain. Um, and no, you are not dumb at all. In fact, just ask questions. I mean, you'll probably even find out that many of the questions you ask, I probably can't answer. um, so the island of stability, that's a great question about what's considered stable and what's not considered stable. In my mind, if it's stable, that means that it will be able to survive in its state for all eternity if it's stable. But I'm unsure if there's a time limit for the stability. But just off the top of my head, when I think of stability for a isotope of an atom, I think that it can remain in that state for either forever or at least for an extremely long period of time, probably like on the order of the universe, on the order of the age of the universe at the very least. Um, so a neutron star. So that's actually a very good question. So a neutron star is a type of dead star. It's produced by what we call red giants. Now the idea is that you start off with a main sequence star. Main sequence stars being a particular type of star that's burning hydrogen at its core, and then over time, eventually it ends up burning up all the hydrogen within its core, and it moves on to becoming what's known as a red giant star. Over time, the red giant star attempts to fight against its self gravity, which is always trying to make it collapse on itself. And eventually, though, I mean, gravity always wins. We get to the point where if the main sequence star was massive enough, it produces a red giant that's extremely massive, and it will continue to try to fuse elements within its core all the way up into the point where it gets to iron, an iron core. At that moment, it can no longer fuse heavier elements. And so now, since it can no longer fuse any elements higher than iron, it's unable to really fight against that collapse that its self gravity is always trying to do, make it do. So it collapses on itself, and this produces a neutron star under the conditions that the main sequence star that started this whole process would have to have a mass somewhere in the range of definitely within the range of 10 to 20 solar masses, but could be as low as 8 solar masses, and probably a little bit more than 20 solar masses. But yeah, neutron stars are basically just a dead star. They no longer fuse anything within its core. So, Finring is bringing up something that's interesting here. So, hypothetically, there could exist fairly stable elements. And so, stability in this situation could be on the order of years. Okay. That completely changes my ideas of what stability is now. Definitely loving the discussion that's going on in the chat right now. So, right, let me actually get to the main portion of this story. And so, there were some scientists in Japan. At least that's what the story is telling me. But basically, there's some scientists in Japan. So a research team, let's see, at the National Astronomical Observatory of Japan, basically proposed a new formation hypothesis for these particular neutron systems. And so the idea here is that you have you well we'll start off with the idea that in our system we have a neutron star and a red giant. And basically, what would happen is the neutron star is able to strip material off of the red giant. And it can strip enough material. I mean, the idea seems to be very basic here. It can strip enough material such that when the star does go supernova, the supernova is not as powerful, and it's so that the system can also remain stable after we end up getting our neutron pair for the system. And so as it reads here, let's see. This idea is known as the ultra stripped supernova. Excuse me. Um, and so yeah, it states here a research team including Takashi Moraya, I hope I'm pronouncing his name correctly, at the National Astronomical Observatory of Japan proposed a new formation hypothesis where the gravitational force of the neutron star formed during the first supernova strips most of the outer layer of the remaining star. That is the red giant that's now within the system. When this ultra stripped star then explodes, the supernova has much less ejecta, which is less meaning it's less powerful, and the system can remain stable. And so they've named this second type of supernova an ultra stripped supernova. Um, and so and given this hypothesis, of course, or given this hypothesis, these assumptions about these systems, at the very least, it allows for people that are going to be looking for these systems to look for systems that kind of fit the criteria that's going to be expected for the system. And so it goes on to talk about how, given these predictions, a team led by Kashala Day, at a PhD student at Caltech, or the California Institute of Technology, searched the data archive of the Intermediate Palomar Transient Factory, and was able to and found a particular system um, in which there was a supernova in which the brightness evolution and the spectroscopic features of the system kind of matched what would be given by the prediction that you'd be able to make given the scenario that the research team at the National Astronomical Observatory of Japan was able to hypothesize. And so this is actually pretty all very, very interesting. So is there any characteristic about the first star that can be looked for? That is a very good question, right? Um, However, in order for you to in order for you to be able to determine if the first star is heavier than what it should be, you need to know about the mass of the progenitor star. That is the main sequence star, um, the initial main sequence star that was used to produce the neutron star. So, for example, if you had a main sequence star that's, let's say, and I'm just throwing numbers out there, just to make the point. You had a main sequence star that was 12 solar masses, and this produces, on average, a neutron star that's 2 solar masses. And you knew that this was the case for the system, that the main sequence star that produced the first neutron star was 12 solar masses. However, you see that in this particular system, instead of it being a 2 solar mass star for the first neutron star, it's actually somewhere around 2.4 solar masses. Then, I mean, in that situation, you'd probably be like, "Oh, this is abnormal." Of course, you'd have to compare that to whatever sort of statistics that you generate from 12 solar mass main sequence stars producing like a bunch of neutron stars that are on average 2 solar masses. You need to know the standard deviation of that and some other stuff. But I think you need to know more information about the system before it became a neutron star. So I'm not too sure if we'd be able to test for that. But at the very least though, you could look for these systems where, given the fact that the neutron star is stripping material from the other star in the system, assuming it's a red giant, you can look for systems, and I believe they even stated here that the spectroscopic features they're looking for specifically. Right. The detections of ultra-strip supernova. No, let's see where else they were saying this at. Could have remember reading that. Right. The spectroscopic features closely matched Mariah simulations, including hints of diffuse helium envelope. Um, and so I would imagine, though, I mean, if you have this neutron star and this red giant, and it's stripping material, it's stripping the outermost layer, which is more than likely composed of hydrogen. And so, if you're seeing these systems where spectroscopy is kind of revealing that the companion star of the neutron star is a red giant, and it seems to have lost the hydrogen content in its outermost layer, then I mean that would be one sign that this system might be one of these systems that fit the hypothesis that's been stated here. So how come most neutron stars on this around 1.3 solar masses? So, and that's a great question actually. So I would assume that the minimum mass of the neutron star would probably be somewhere around 1.4 solar masses. However, what they're probably not stating here are the errors on the. Let's see. Let me look at this list actually. What they're probably not stating are the errors on these mass calculations. So let's go back. Let's see if this other column has like error information. No. So there's probably an error on this, and I don't know exactly how much the error is, but the error might put it within the what's considered to probably be like the more acceptable zone or mass region in which neutron stars live. Yeah, what Haney states is very true. HR diagrams are are if you're able to understand an HR diagram, you will understand what a neutron star is, and also, of course, what other types of stars there are. Well, actually, when you think about an HR diagram, they typically don't show neutron stars. I mean, they you can place neutron stars on there, but I believe it'd be very. I think it's very difficult to do so. Typically, when you look at an HR diagram, of course, you'd see the main sequence, you'd see the red giant stars, and you'd see white dwarfs. But typically, they never really place neutron stars on there. But definitely, being able to understand the HR diagram and understanding the death of stars, it makes it a little bit easier. But yeah, Finring, I mean that's actually right, really interesting. You're right. Most of these stars are like right there, close to the Chandra Sekhar limit for white dwarfs. And it was always my understanding that like 1.4 solar masses is like the minimum mass of a typical minimum mass for neutron stars. Hmm. So did I miss any questions from above? Or does anyone have or does anyone else have any more questions? But yeah, guys, so I think, and I'm quickly talking to Susie. Um, I might be doing Mondays. I might be doing another stream on Monday for Daily Space because I also believe on that day as well. Um, Pamela and Andreas will be traveling. All right. Well, I look forward to it. Like I said, guys, I mean, whenever we have these conversations, I mean, I love what I do, but it's definitely like a nice little way of escaping, my other work that I'm doing, to be able to sit down and like think about a problem and try to think things through, and then be able to come here and discuss it with you guys. So, Hanny asks, what happens with any planets in these systems? So, that's a great question. Um, I would imagine that the planets within the systems are going to be cooked. One, by the first, if not, well, definitely by the first supernova, and then definitely by the second supernova. As for whether or not they'll be ejected from the system, that's a great question. That would be a great question, and I believe the equations and the math that I presented earlier would kind of be a nice start for being able to see if the situation would be that the energy from the supernovas could somehow push the planets out. I don't. I'm not too sure if they'd be able to, if a supernova would be able to, at that close range, would destroy the planet, completely. Of course, you could always determine that by first starting off by calculating the gravitational binding energy of the planet, which is basically just that equation I kind of like the equation I showed earlier. The G times m squared divided by r, and you can compare the total amount of energy output to from the supernova compared to the amount of energy it would take to kind of like break apart the planet, which would be an interesting calculation actually. And so you say, is this what could have happened to? I'm not gonna lie, I don't know what that planet is. I'm gonna look that up now. Is this supposed to be a planet that was in another? Oh, I see. let's see, is a mildly active comet. Not a planet, it's a comet. Oh, cool. So, if I'm understanding your question, so are you asking? So, if I'm understanding this, are you saying that, and given what Finnering just stated there, are you saying that within a system within our galaxy, there was a supernova, and the supernova ejected the comet, and the comet just so happened to come our way and entered our system? Oh, that's interesting. Honestly, I don't know. I mean, like I said, the very first thing I would do, as far as calculations are concerned, it would be that I would calculate. So let's see what's currently showing. Okay, I can use that page. So the very first thing I would do, and they actually have done some calculations. So this equation that's shown here would be where I would start. I would calculate the gravitational binding energy of the planet, where m is the mass of the planet, r is its radius, and the 3/5 that factor comes from the fact that it's spherical. And then I would see if the energy output from the supernova, that fractional energy, would be enough to be able to break the planet apart. I think that would be a pretty cool science mission to follow a comet and like find out more about it. Because of course, if this is the situation, it comes from a different system. You know, the comet itself would probably would shed some light on some of the materials that were produced within that system. Especially like for example, if the comet is like from a planet, it'll let you know at the very least. Of course, assuming the comet came from a planet, that what the planet was composed of. Well, guys, I really enjoyed today's discussion. I hope you guys did as well. And so I'm thinking I will be back on Monday with another daily space news update, and I'm probably going to, of course, mix it up and do a little bit of Astro 101 with it with the calculation. And so I look forward to seeing you guys then. And again, thanks for tuning in. And I wish I could end like Andreas and Pamela with a really cool ending, but I'm just gonna say bye for now, and I'll see you later. And I look forward to seeing you again with the next stream. All right, guys, bye.